Hello and welcome to the algebras. In this lecture, lecture number 14, we will talk about classification of root systems. Let's start with recalling our setup. We consider an Euclidean vector space E with a fixed inner product. Let phi be a root system in E. Choose some basis pi in the root system phi. The number of elements in this basis, which is also equal to the dimension of our space E, is usually called the rank of the root system. It will be convenient for us to fix some notation for the elements in the basis pi, so we denote them by alpha 1, alpha 2, and so on, alpha n. So here n is the rank of phi. Recall that we know from the previous lecture that the scalar product between two different elements in the basis is always non-positive. In particular, the angle bracket between two different elements in the basis, which is given by the scalar product times 2 divided by the square of the length of the second vector, this is also non-positive. We also recall the property of the root systems that the angle bracket between alpha I and alpha j times the angle bracket between alpha j and alpha I is one of the positive integers 0, 1, 2, or 3, if I and j are different. We also recall that the angle bracket between alpha I and alpha I is always 2. Let us start with the definition of the Cartan matrix of the root system phi. The Cartan matrix of phi is defined as the n times n matrix. So here n is the rank of the root system, and the entry in the row I and column j of this matrix is just the angle bracket between alpha I and alpha j. We saw on the previous lectures that the while group W acts simply transitively on the set of all bases. Moreover, it acts by orthogonal transformations, that is, by transformations which preserve the scalar product. It follows that the Cartan matrix of phi depends only on the chosen ordering of the elements in our basis pi, but not on pi itself. A very easy example is the root system of rank 1. If we have a root system of rank 1, then it always have only two roots, plus and minus alpha, where alpha is some non-zero vector, and hence the Cartan matrix of phi is a 1 times 1 matrix, which consists of the number 2, because the angle bracket between alpha and alpha is always 2. The next example is rank 2 root systems. In the previous lectures, we saw the classification of all rank 2 root systems. There are 4 of them up to isomorphism, and they are listed here. And now we can compute the Cartan matrix for each of them. For the first one, which is denoted by A1 times A1, we have the basis consists of two vectors, and they are orthogonal to each other. So we have 2 and 2 on the diagonal and zeros outside the diagonal. For the second root system of type A2, the basis consists of these two vectors, and the angle bracket between them is minus 1. And they have the same length, so the angle bracket is symmetric in this case. So the Cartan matrix has 2's on the diagonals and minus 1's outside of the diagonal. The next root system, the one of type B2, the basis of this root system consists of these two vectors. They have different lengths, and so the Cartan matrix will not be symmetric anymore. So it has 2 on the diagonals, and the angle bracket in one direction will be minus 1, and in other direction will be minus 2. The final root system, the basis of this root system consists of the following two vectors. So this is alpha 1, this is alpha 2. Alpha 1 is supposed to be longer. Again, since the basis vectors don't have the same lengths, the Cartan matrix will not be symmetric. So it has 2 on the diagonals, and minus 1 as one component outside the diagonal, and minus 3 as the other component. So these are Cartan matrices of all rank 2 root systems. The next combinatorial tool associated to a root system is Dynkin diagram. The Dynkin diagram of a root system is a special kind of graph, which is constructed as follows. The set of vertices of this graph is 1, 2, 3, and so on up to n, which is naturally identified with the elements in our basis pi. The number of edges between the vertex I and the vertex j, which is different from I, is equal to the product of the angle bracket between alpha I and alpha j and the angle bracket between alpha j and alpha I. So this graph by definition contains no loops. Finally, in case vectors alpha I and alpha j have different lengths and are not orthogonal to each other, then one marks the edges between I and j by the symbol greater than, which indicates which of the two vertices corresponds to a longer route. So the symbol indicates the direction from the longer route to a shorter route in our basis. Similarly, as for the Cartan matrix, the Dynkin diagram of phi depends only on the chosen ordering of the elements in our basis pi, but not really on the basis pi itself. Again, the rank 1 example is very easy. If you have a root system of rank 1, it has only two roots. The basis pi has only one root, so the corresponding Dynkin diagram is the diagram with one vertex and no edges. Let's now go to our rank 2 example. In the rank 2 case, we have four different root systems. So the first root system is A1 times A1. The basis contains always two elements, and here these elements are orthogonal to each other. So in the corresponding Dynkin diagram, we get two vertices corresponding to the basis elements and no edges between them because the basis elements are orthogonal to each other. The next root system is the root system of type A2. The basis of this root system contains two elements, so we have the graph with two vertices, and the angle bracket between the basis elements is equal to -1 in both directions. So there will be -1 times -1, exactly one edge connecting these two vertices of the Dynkin diagram. In the root system of type B2, we again have two elements in the basis. One angle bracket between them is -1, another one is -2. So there will be -1 times -2, two edges connecting these elements, and the symbol greater indicates which of the basis elements is longer. Finally, the root system of type G2 again has two vectors in the basis. The angle brackets are -1 and -3, so there are three edges between these two elements, and our symbol indicates which of the basis elements is longer. So these are Dynkin diagrams for all rank 2 root systems. Now we can formulate the main theorem. The claim is that the Dynkin diagram of an irreducible root system is one of the following 9 diagrams. Actually, there are 4 families of diagrams depending on a parameter n, and there are 5 exceptional diagrams. The diagram AN, with just a line like that, the diagram BN, which differs from AN by a double edge at the last step and certain disposition of our mark greater. CN is the same as BN, but this mark is reversed. DN has a triple vertex. F4 is a root system of rank 4 with double edge in the middle. So G2 is a root system of rank 2 with triple edge. And then we have 3 more root systems E6, E7, and E8 as indicated here. To avoid repetitions in this picture, we need to assume that for AN, the parameter n is a positive integer. For Bn, the parameter n is at least 2. For Cn, the parameter n is at least 3. And for Dn, the parameter n is at least 4. The remainder of the lecture is dedicated to a proof of this theorem. So we let gamma denote the Dynkin diagram of a root system phi. We assume that phi is irreducible. This means that gamma is a connected diagram. We start with certain preparations. First of all, denote by Vi the normalization of the basis vector alpha I. That is the vector alpha I times the scalar 1 divided by the root of the scalar product of alpha I with itself. So the vector Vi is normalized, its length is 1. Observe that from the properties of the root systems which we know, it follows that 4 times the scalar product of vi and vj squared equals exactly the angle bracket between I and j times the angle bracket between j and I, and hence is a positive integer 0, 1, 2, or 3. And this is true for any I different from j. Therefore, from our definition of a Dynkin diagram, this number 4 times the scalar product of vi and vj squared is exactly the number of edges between the vertices I and j in our diagram gamma. Our first important observation is that the number of pairs I less than equal to j, such that the scalar product of vi and vj is non-zero, is at most n minus 1. This means that there are at most n-1 pairs of vertices in our graph gamma, which are connected by some kind of edge. The edge can be double, triple, and so on. Proof. Consider the element v1 plus v2 plus and so on plus vn. So this is a linear combination of the elements of our basis with non-zero coefficients. In particular, it is non-zero. Now let us compute the scalar product of this vector with itself. Using the additivity of the scalar product and the fact that all the i's have lengths 1, it follows that the scalar product of v with itself is equal to n, this is the sum of the lengths of all involved vectors, plus 2 times the scalar product of vi and vj for all pairs I minus j. Since v is a non-zero vector, this expression must be positive. In particular, the number n should be strictly greater than or equal to than the sum over all pairs I smaller than j of the expression minus 2 times the scalar product of vi and vj. Now, let us recall that the scalar product of vi and vj is non-positive. Therefore, the expression minus 2 times the scalar product is non-negative and hence coincides with the square root of 4 times the scalar product of vi and vj squared. And as already noted above, 4 times the scalar product of vi and vj squared belongs to the set 0, 1, 2, and 3. So in the situation where the scalar product is non-zero, the value of this expression is 1, 2, or 3. Therefore, the value of the square root of this expression is at least 1. Therefore, for each pair I less than j, such that the scalar product is non-zero, we have a value at least 1 in this sum. Consequently, the number of such pairs should be at most n minus 1. One nice consequence of this lemma is the fact that the graph gamma has no cycles. Indeed, assume that gamma has a cycle. Let phi prime be the root system in the intersection of phi with all simple roots involved in the cycle. In other words, we simply assume that the cycle connects all simple roots. Due to the cycle, the Dynkin diagram of phi prime has at least as many unoriented pairs of vertices connected by an edge as its rank. Indeed, if you have a cycle connecting k vertices, then this cycle has at least k different pairs of vertices which are connected with each other. But this contradicts the previous lemma, hence applying our corollary. So from now on, we know that our graph gamma is acyclic. Our next observation is that each vertex of the graph gamma is incident to at most 3 edges. Let v be one of our elements v1, v2, and so on, vn. Denoted by w1, w2, and so on, wk, the vectors in the same set which are connected to the vertex of v in the graph gamma. Since gamma has no cycles, and w1, w2, wk are all connected to v, they cannot be connected to each other. So they are, in fact, an orthonormal system. So let's complete this orthonormal system by another vector u such that the outcome forms an orthonormal basis in the linear span of these vectors together with v. In particular, from the Gram-Schmidt method, we know that the scalar product between u and v must be non-zero, and hence the length of the vector v with itself, which is 1 by our assumptions, is also equal to the sum of squares of scalar products between this vector v and elements of our orthonormal basis. And since the scalar product of u and v is non-zero, if we take away the corresponding summand, what is left is the sum over I from 1 to k, the scalar product of v with wi squared. This sum is strictly smaller than the scalar product of v with itself. That is strictly smaller than 1. At the same time, as we already noticed before, the square of the scalar product times 4 is exactly the number of edges between the vertex of v and the vertex of wi, which means that as soon as we have one edge here, the corresponding summand contributes with 1 over 4. If you have two edges, it contributes with 2 times 1 over 4. If you have 3 edges, it contributes with 3 times 1 over 4. So the total number of contributions here can be at most 3, which proves exactly the claim of this proposition. One interesting corollary of this proposition is that if our diagram gamma has a triple edge, then gamma equals the Dynkin diagram of type G2. Indeed, each vertex is incident to at most 3 edges, so no other edges from any of these two vertices are allowed, and since the diagram is connected, it must coincide with this diagram. So there is only one Dynkin diagram having a triple edge, and this is a diagram G2. In order to exclude all other possibilities apart from the original list of Dynkin diagrams, we have to study forbidden subgraphs in Dynkin diagrams. So from now on, let us assume that gamma has no triple edge. The claim is that none of the subgraphs given in the following list is a subgraph of gamma. The first graph is the type AN line, which has at both ends double edge. The second graph is type DN diagram, which has a double edge on the opposite end from the triple point. The third graph is a DN type diagram with triple edges on both ends. The fourth graph is a type F4 diagram with one extra edge. The next graph is a type E6 diagram with one extra edge. Then we have a type E7 diagram with one extra edge, and the type E8 diagram with one extra edge. So this list is designed more or less such that if we take away one edge, we end up in a Dynkin diagram. And what we want to do, we want to prove that none of them is allowed as a subgraph of our gamma. The shortest way to prove this is to check the following. We are going to present for each of the above forbidden graphs coefficients of a certain vector and the coefficients given in the basis of simple roots, such that the lengths of the corresponding vector computed with respect to our scalar product is 0. And all these vectors will have non-zero coefficients, so the vectors are non-zero, which manifestly gives us a contradiction because our scalar product is positive definite. So the claim is that in the first case, when the AN graph is extended by double edges on both ends, so we have 3 different ways to distribute the less than or greater than signs on the double edges. And in these 3 different situations, we should take the following vectors. So if the less signs are distributed in this way, we take a linear combination of positive roots with these coefficients. So if the less signs are distributed such that the middle is greater, we take the linear combination of positive roots with all coefficients 1. And in the final stage, if the middle part is the smallest one, so we put 2 there and have 1s on the ends. And the claim is that the lengths of the corresponding vectors for the corresponding scalar product is 0. We will give an example of the computation at the end where we present all these counterexamples. For the next type of graphs, where we have a double edge added at the end of the DN diagram, so you take these kind of vectors depending on the direction of the double arrow in the diagram. In case we have an extension of dn by triple h on the other side, we take the middle part equal to 2 and 1s at the roots of the diagram. In the extensions of the F4 diagram, again, we have 2 cases depending on the direction of the double edge. they're given here. In the extension of type E6 diagram, we have this quite symmetric version where you have 3 in the triple point and then you gradually decrease by 1 when you go farther away from the triple point. In the extension of E7, we have the following coefficients. And finally, in the extension of E8, we have the following coefficients. Let's compute one example, and this is the very first situation. This situation, when the type A part is reduced to only 1 point, so the coefficients then should be 2, 2, and 1, where 1 corresponds to the longest root. So we have 2, 2, and 1. So let's compute the scalar product of this vector v with itself. So the vector v is equal to 2 alpha 1 plus 2 alpha 2 plus alpha 3, and we take the scalar product of this vector with itself. Using the linearity of the scalar product, we can rewrite it as a sum of 4 times the scalar product of alpha 1 with itself, plus 4 times the scalar product of alpha 2 with itself, plus the scalar product of alpha 3 with itself, plus 8 times the scalar product of alpha 1 with alpha 2, plus 4 times the scalar product of alpha 2 with alpha 3. So now alpha 1 is the shortest root. Let's assume that its length is 1. Then 4 times the scalar product of alpha 1 with itself will be 4 times 1. The root alpha 2 is longer than alpha 1, and together they span a root system of type B2. The length of the root alpha 2 is square root of 2 times the length of the root of the alpha 1. So 4 times the scalar product of alpha 2 with itself is 4 times 2. Similarly, the last root is square root of 2 times longer than the second root, which means that it is 2 times longer than the first root. So the last expression will be just 4. Again, the scalar product of alpha 1 and alpha 2 is equal to minus 1, because this is what happens in the root system of type B2. The scalar product of alpha 2 and alpha 3 is equal to minus 2, because it is minus 1 what happens in the root system of type B2, but here the roots are square root of 2 times longer than the corresponding roots in the root system of type B2. Therefore, it will be minus 4 times 2. And when we compute this expression, we get 0, exactly as claimed. So similar computation is valid in each of all other cases, and put together, in each case, we get a contradiction with the fact that the scalar product is positive, definite, thus proving the claim of the proposition that all these subgraphs are forbidden as subgraphs of Dynkin diagrams. So now we can prove the main theorem. The subgraphs which we constructed are constructed such that if you extend one of our Dynkin diagrams by 1 point, such that this is no longer one of our Dynkin diagrams, we end up in one of those forbidden subgraphs. This means that the only Dynkin diagrams without any triple arrow or any of the forbidden subgraphs are our Dynkin diagrams of type A, B, C, D, E, and F. And we already saw before that the only Dynkin diagram with a triple arrow is G2. So this completes the proof of our main theorem. Thank you very much. Hope you enjoyed the lecture.